Hello, gentle readers. It's October 19, 2025. Yesterday was October 18. And so in Logos 2000 today, it'll be just continuing as of the previous conversation, which was as with regards to software. And so in the context of Logos 2000 and the discorso logos and the notion of the word and logic and all the associated terms, then software is just kind of the large-scale embodiment of that in today's settings, like the modern information technology systems of the enterprise environment and all such matters of commerce and transport and government and data, the data. As with regards to the embarrassment of computing resources as so afforded by 20 or 30 more years of Moore's Law, who is one of these people at Intel Corporation who's noticed that things are doubling every couple of years, and so kind of subscribed to that the capacities and the costs were increasing and decreasing respectively by half, or year over year by twice, irrespectively. That's the embarrassment of resources, because what costs something like a million times as much a mere 30 years ago cost 1,000,000 times less than it did then. And so the economy of that, and then makes for this economy of ubiquity, because it's not like not a monoculture. It's very much a monoculture, because the economies of scale make this economy ubiquity, and so everything's really the same. And so at the same time that makes it so difficult to make anything new, it makes it possible to make lots of things new, because now that ubiquity of scale cannot change that readily. And so things can just be built that take advantage of the economy of ubiquity, this monoculture, and arise to be very much being a new sort of thing. So that's kind of the idea here, is to just kind of try and talk some more about software, and then the import, meaning the importance sometimes, be the import and export of things, the importance of language and words, as after reading comprehension, a writing command, in a sense, that these become very scalable, I guess one might say, skills. Then as it becomes so that once somebody gets above being, kind of a mere coder and up into being, a little bit more than a garage band, and then taking part in some of the great enterprise, yet to be able as an individual to kind of pull stuff together, that it really can be, the infinity times coder. That's kind of the goal. I'm not that great of a coder. Am I a real programmer? Well, I've in various stages of approaching the learning curves and the learning hills and the learning mountains of the learning curve, which is the general idea that something is easy to pick up and then gets harder to learn, to go up the learning curve. Hopefully that at some point in time there are these plateaus of the learning curve. That beyond the great learning hills, there are great learning mountains and this great learning range of all these things. Yet at the same time, it's not really as so when somebody said hundreds of years ago, and hundreds of years ago before that, hundreds of years ago before that, and hundreds of years ago before that, that everything has already been done. It's all been done before. And nobody's ever going to know all of physics or science anymore, or mathematics, because there's just too much of it. Because there's still so much of it that people can know all at once, pretty much, that make it so that then the idea of foundations and being able to encompass, embody, and relay that to you, among us, and as a general sort of enterprise that such that endeavor and enterprise exists, is not that far afield. And so then in these sorts of accounts, the idea is to relay this sort of notion and to make it so that another could as well employ these same sorts of concepts for the eventual results of things like the paradox-free reason and the sufficient and thorough reason to really be confident that there's if it's all been done before, at least At least it's been done once that this kind of thing exists. So today, all I'm going to do really is just kind of finish up this last box of books that were being absorbed and considered with these random sort selections. And I've read these books before. I mean, I've at least leafed through every page and put them before my giant scanning eye that I have here with its capacity. And then they'd be able to go through these things and exercise a lot of them and of course the day-to-day work. Being an enterprise software developer for 15 years at least, say, in larger sorts of successful, I guess you might say, of these concerns. Then there's just this other box of books here, because as Logos 2000 is reaching to 52 videos is kind of the goal. That kind of being the number of cards in a deck of playing cards, usually a poker deck vis-a-vis a pinochle deck, or otherwise the usual cards. That then Logos 2000 will be able to wrap up as kind of in the middle, having been with the foundations briefly a bit, and then the surrounds just kind of either way is coming from the start of the 20th century, considering it and winding up at the medieval philosophers, and then forward again into the modern day account as is presented here in a sense. And then with this various considerations, and as with regards to Quine and Descartes and these sorts of philosophers, and there hasn't really been much yet made of Leibniz, but there is plenty to be made to see his central roles in like the universal grammar and these sorts of things. With regards to something like the square of opposition and the Logica Universalis efforts, the modern day accounts, as after things like Kolmogorov's unexplored intuitionism and Lutwidge-Brouwer and these kinds of things that can be related and attached here again as constructionism and intuitionism turn each other over and will constantly do so forever. That if it's always been this way, then it'll always be that way, and that's how things are. So these first two books are part and parcel of an undergraduate curriculum in computer science. So computer science is the study thing. Why not call it computer engineering? Well, computer engineering is for the electrical engineers that make computers. And so with regards to power electronics and digital information or signal electronics, they're two kind of different things. Then computer science and computer engineering are two kind of different things. Because on the one hand, they both are talking about resources and projects and systems and implementations and all these kinds of ideas that go into the application of computing technology to provide value of the sort that reduces a cost or enables a functionality of these kinds of things. Or to explore in the novel to introduce new sorts of opportunities in the ideas and as about the language of these things, and so that computer science then has at least two things that are usually parts of the courses, and one is algorithms and data structures. And this is where, like, if my roles titles were stuff like software engineer 4. Or lead in these large tech-driven things, or temp, or whatever. Everybody's expected to know all the different algorithms and their data structures as they're usually known, and their time and space asymptotics, or big O notation, theta notation, big O and little o and theta, with regards to these things, and also with regards to things like time and space, particularly, and linear speed up and these kinds of things. And as with regards to given a perfect distribution, one can define adaptive data containers that automatically model it perfectly, kind of like all these neural net approaches claim to attain to. But given any sort of overall distribution of the data, they have an unknown character to them, and so it's often possible to take even some of the usual tropes of algorithms, like that. Well, it's constant lookup under a hash table by the time you get to the code. We're using the B tree under the B tree, and then it's like, well, it's binary, You know, it's binary search and these kinds of things. That's what I look at today. Is just a little bit first is these two books. Benjamin C. Pierce's Types and Programming Languages. And then this is just the MIT text called Corman, Leserson, Riveston-Stein, or Introduction to Algorithms. So this book of about 800 pages is got all these kinds of algorithms, and we could start with things like you know, arrays and lists and associative arrays, and they're discussed here quite some time ago, and then into trees and directed and undirected and cyclic and acyclic graphs. So trees are a critical, usual sort of higher level data structure that everything else in programming so often is just sets or lists and these kinds of things. And then with regards to their algorithms and permutations and combinations and everything after formal methods and finding things or enumerating things and the combinatorics, this is part of concrete mathematics. Talks to or about somebody like Knuth's great work in tome as after that. That might be in one of these following boxes. That here it's this is the kind of thing that is the bread and butter of computer science or programming. And so everybody would be expected to know that as with regards to the usual sorts of accounts of all these usual kinds of things. And then with regards to, like, you know, the forms and the expressions and the recurrence relations, those are tough to figure out. And that the recurrence relations particularly end up being when you start writing out numerical methods, it ends up being after the first few iterations, the handwritten derivations just reach out to page after page after page of these things. And they do in the algorithms as well. Yet there's so much of it is just basically the surface of the routine, and given that as kind of an opaque interface with the descriptions of its time and space complexity. And so, like, with regards to whether to use an array or a linked list, with regards to the search and the random access and the maintenance of those kinds of things, with regards to the different use cases of these data structures, their algorithms, and what data structures to pick for what algorithms, that's basically just a few sheets. And according to any given particular A to B exchange, transition, or generation of data is kind of one of those. Keeps it simple that, yeah, this book in a sense can be reduced to a few pages, or say an index card that one would be allowed to bring along to an exam, or a coding interview or something like that. That those things are almost always supposed to be closed book, because to be a true test and exercise and an exam of somebody's ability, it's they got to be able to explain all that stuff. And then supposedly we're supposed to be able to come up with all these recurrence relations kind of automatically, and they just kind of drivel out in a sense. And that's so. For like connected components, same component. Like identity and the trivials and the vacuous cases and all this kind of stuff. Linked list representation of disjoint sense, getting into graph theory, so that then for lattices and graphs, the graphs have the greatest sort of language in the descriptive, because then there's also so many cases with regards to the state and their perspective and the distances, and these things are like traveling salesman problem, and other questions is of after the polynomial time, the non-polynomial time. That as well, there's then the approximations and these kinds of efforts and results that get into those. And then whenever it's not really a general case, that there's pretty much always kind of a special approach to break the otherwise asymptotics of many usual sorts of algorithms. Types are, and the transitivity of types, and the associativity and these other kinds of words, but the algebras has that those kind of properties aren't necessarily so much about the algebras when they're considered a piece. And so types and the lambda-calculus, as it's called, if there's the process and pi calculus for communicating sequential processes like a finite state machine and its general description as a graph or a network in flow. Then the types and the lambda calculus help to show that a given thing and under a given transformation of this and that and the other thing, according to the objects and the types usually in the programming languages, the types and type theory is just a great thing to have as the implicits and also as a formal, so it can be so established that, for example, in a strongly typed language, that thusly one can always be able to show that according to the language that given things will be a so. So type theory is a little bit after algorithms and data structures, and if that's a little bit after structured programming itself, then the type theory is just a great thing. And so this book was the first one I found of a large textbook developed to present type theory, and it's in this basic operation of types compose, and so that this and this and that result transitively a type of a thing according to the derivations. That is a pretty great thing. Lambda calculus, untyped lambda calculus. Perhaps the best illustration of the power of recursive types is the fact that we can embed the whole untyped lambda calculus in a well-typed way into a statically typed language with recursive types. So this is just saying that it's a no-op. A no-op is a short word for a no operation, meaning that it's like, well, we abstractly would always be invoking something, but nothing happens. Nothing can happen. What is it? Well, it's a no-op. And so it's just usual placeholder for otherwise that in another abstract routine is like, well, yeah, if the case is like so, then it must be this precondition hold. Constraint-based programming and pre and post conditions with regards to languages like Eiffel that have strong types and also strong conditions associated with the assertions they make about the state according to the scope of the module, the body of the runtime. That this sort of idea just says, well, look, here's a trivial case. Isn't it funny how that always runs out? Let D be the following type: D equals mu x dot x goes to x. Define an injection function, LAM, lambda, mapping functions from D to D onto elements of D as follows. So this is the type is a function of type itself. So there's a type and then the relations. So here it's all relations. It's like, well, these two objects are related by being of the same kind. These two objects of different kinds are related by, according to this particular function, they also have resulting this possibly third kind that results from them, or any number of these things, any tuple of any number of input parameters, for that matter, any number of outputs, that being a sequence or a tuple or set associative of the description of the relation that a function defines according to its domain, I would say, vis-a-vis the image or the members of the relation. That this is kind of like to show that showing that functions are their own sorts of types themselves. And here that's just given to be a function is a matter of program routine that given inputs produces outputs. And so it's kind of got the input process output and the algorithm on the data structure associated with it. But it's really just according to its signature, and that's all there is to it, because that's all it really defines. With regards otherwise to the side effects, as with regards to modifications of variables outside the local scope, and those being visible to both scopes and these kinds of things. All quite usual, you know. Lambda, so and then he says lambda f is so he's defining the function as a type. Apply one element of D to another, we simply unfold the type of the first, yielding a function, apply this to the second. So this just helps to show that, just kind of like that consumers and producers pattern, the idea is like, well, there's a given and there's a result. There's a given and a result. That this is a way to help just establish that's one of the fundamental relations in type theory, is this kind of thing. Subexpressions, programming languages, the meta-theory of recursive types. I was going to say recursive trees. The meta-theory of recursive types. adding this rule would not be a good idea if we want to keep the existing evaluation semantics. So that gets into then with regards to types and then escape from types, people using void types or uninterpreted data like strings to store everything around. Is this possible to give every different kind of, usually it's declared as a string or for that matter an auto or something like that, a var, as an object is what they may be in various more loosely typed programming languages. That it's another idea is often is like, well, how about give every string its own type? And for a language like Java, then it says, well, you can write that to char sequence. And then at least almost all the functions that work on string also work on that. Because in Java, there's only one string class and it's final, meaning you can't extend the string class according to the built-in the runtime and how it handles sequences of character data. And it's fine, and this is the way it is. But then with regards to then treating those as types is that every value is its own type. Of course, abstractly, any given individual anything is its own type. And about things like the theory of ramified and stratified types. And then this book was written by Benjamin C. Pierce, P-I-E-R-C-E. There's a fellow from the 1800s, Pierce, P-E-I-R-C-E, who really kind of brought the theory of types in its initial form. And so he's really highly regarded is Pierce. Charniak and McDermott's Introduction to Artificial Intelligence. I thought they said that AI was just invented a few years ago, but this is a book called Introduction to Artificial Intelligence from Addison Wesley from 1985. So just like all these other books being read about here about neural nets and expert systems and statistical inference, this is a book about AI and Haugland's AI, which is like, well, it's not just smart anymore, is genius the thing, these are the kinds of things. Well, the preface begins, well, we have no evidence. We suspect that most professors write textbooks because they're going to teach a course for which none of the existing texts are suitable. Whether or not this is typically the case, it was certainly the reason for the book you're now holding. There are three things we wanted from a text on artificial intelligence, from now on AI. And some people will say synthetic intelligence, other collective intelligence, others emergent intelligence, others mechanical inference and intelligence. The authors go on. It had to include those aspects of the field which we felt would prove to be enduring. For example, low-level vision research, which is given short shrift in most AI textbooks. It should present AI as a coherent body of ideas and methods, drawing on the work of the last 20 years. See, here in 85, it's already like from 1965. But translating it into a more uniform set of concepts, favoring clarity over journalistic accuracy. So most of the things about the latest, greatest way to like make AI, whether it was like, run these neural net regression models. How about a generalized linear model? How about a principal component analysis? It's like, no, those are too technical. We're just doing neural nets and power laws because they apply to everything and often give something, to like the latest is like, well, how do I program it? And what is it? Is like, well, it takes the whole body of Google and all the other search engines to make one, and then they all have to make a giant thing to have one, and then it's got to be online all the time, and that's what we have, and so that's what we're selling, and that's what you should buy, and that's how you should align your efforts to be included and these kinds of things, and it's kind of like, well. That's not really so. It's kind of so pragmatically, and it's kind of so as of the zeitgeist, meaning in the sense of the times, but it's a little underinformed and a bit shallow, say. Not to say that that's wrong, because everybody's got to start kind of at the shallow end, although some prefer kind of be thrown in the deep end, as it were, to learn how to swim and not drown. But these are kind of the ideas that, as this textbook goes to explain, is that all this stuff about AI, 20 years before this book was written, this book was written 40 years ago already. So 60 years ago already, all this stuff about the AI hype has that AI hype itself is a very, very uh, old idea. So the success of AI and the success of data and information systems is indisputable. If it wouldn't have been for the economies afforded by information systems, then it would not have been possible to maintain the standard of living for like the entire economy for a long, long time, because it's simply the value present would not have been so. Then for the years, and this was before the dot-com boom, and it was not the large corporations, it was mostly the government. And on behalf of the common good and the people, one can only hope. But then after that, and then so much money went into, after Moore's Law and the economy of scale, besides helping hold up the pillars and foundations of the economy and these kinds of things, that it just goes to show that there is a lot of value, and now there's so much of it available that it could really be a very Pollyanna sort of great. I hesitate to say utopia because that's always used to introduce the dystopian, and always used as an advertisement for things which are almost entirely charades and otherwise, you know, the promises that can't be fulfilled, and unreasonable expectations. But it is so that still there's so many different ideas and technology that can come out that it can be a good day for everybody at some point. The authors go on, it should present AI as a coherent body of ideas and methods. And 3, it should acquaint the student not only with the classic programs in the field, but the underlying theory as well. Mathematical logic for knowledge representation and inference, linguistics for language comprehension, etc. So here it goes to show, it's like, well, what's the AI? Is it a large language model in a vector machine according to an entirely inscrutable, massively layered neural net apparatus? It's like, no, it's thinking and reading and writing and talking about it. It's the language and the logic. In brief, our belief was that AI is distinguished by its subject matter, not its history or methods. Its subject matter is the mind, considered as an information processing system. So yeah, this is a technical bit. Here's technical, I suppose. Here's the result. Writing a textbook is the idea here. And so this guy here is like, they kind of describe the order of reading this book, and it's a flow chart, a graph. If after the idea of the first talk on this software is like a pseudocode, and the second talk was that it's mind, and then the third talk is kind of like, well, it's a flow chart. It's a finite state machine or a flow chart or a diagram. It's these things that both it itself, the running software, and the deliberation and contemplation of its artifacts and the representations that are relatable and these kinds of things. Chapter 2 is in parentheses because readers not interested in programming can skip it. And so this just gives a way of reading things. So then it has chapters like so. AI and internal representation. So what's its view of the world according to its own internal representation. Lisp. So Lisp is like the language of Lisp, and a lot of the AI research was in this language. And it's in the functional routines. It does recurrence real nicely and neatly. It does recursion real nicely and neatly. That said, so in some sense it's elegant, it may be so called. That said, it's also kind of inscrutable. So when you get into stuff like Haskell and Lisp, they're often deemed great pure languages. They're also about as remote from usual natural languages can be. Now, I imagine I could get some flack from like fans of Emacs and stuff about that. Yet, that's okay. It is what it is. Vision. So it's talking about like how to implement vision, and from one sensory apparatus that's just entirely agnostic, except what a stimuli is, to matters of experience, because and it's a common shared experience, vision, because light is non-judgmental in a sense, and it only always is accordingly to physics entirely only as influenced by the matters of real representation, it may so be, for vision and matters of mental models, that there's vision as to like what is that in terms of then what results in image, and from that image what results its elements. With regards to something like René Magritte's the trees and the images or whatever, ceci n'est pas une pipe, meaning he's like, here's a picture of a tobacco pipe, and but it's just a picture. It's not the thing itself. Whether it's with regards to machine vision, there are examples, for example, is that machine vision systems were being tested, and what happened is like, well, it was designed to detect, say, a picture of a cat. And so somebody just walked out in the field and unrolled a poster of a cat, and lo and behold, it made its world that way. So talking about computer vision as a matter of computer senses and the stimulus, and with regards to the out of band sort of notion of that, is most people's lives do have experience of not believing everything they see, or when it's surprising to actually to confront it with their reason. As with regards to saying, for example, like, oh, that UFO I thought I saw, actually I can see now that it is a weather balloon or something like that. Not to say that there's not any sorts of ideas about that. And similarly, it's like, well, I can't see anywhere that absence of evidence isn't evidence of absence, but I know it's something like the theory of light itself, or these kinds of things. So a model of intelligence has got a model of reason and a model of experience. And so that's just another thing to get figured out with regards to these things. Parsing languages, chapter 4. So that's another great part of the discourse. Search, logic and deduction, memory organization and deduction, abduction, uncertainty, and expert systems, managing plans of action, language comprehension, learning. So a book of this sort is as profound and correct and true today with regards to the latest, greatest AI as is. And that's why this sort of enduring kind of approach to the knowledge and the relaying of the knowledge is deemed necessary for these kinds of things. And so then to compare something like this to like Russell and Norvig's book Artificial Intelligence, which gives algorithms and pseudocode for a lot of different kinds of search and heuristics and goals and their reward functions usually of how to pick a winner and this kind of thing. Has something like that is almost entirely dedicated to just like how one might say plan to copy that and result something that is at once within the bounds of that and limited to the bounds of that. Whereas something like this is at least a little bit more like, as much as you can be intelligent yourself, we're trying to figure out how we can be intelligent together, courtesy our machines and how they are. All right, the rest of that box of books here. So Oxford Dictionary of Statistics. So statistics is if there's these three legs of machine learning, and one of them is expert systems, and another one is neural nets. So a discrete closure of categories, the expert system, an abstract flow machine that, according to its conditions, will just result that, according to random variation, will eventually settle on a routine that can usually match one, and it can do that unattended and basically, according to the speed of computers, billions and billions of times till one finally survives. I mean, that's like back to the old metaphors of the gaff and these kinds of things in some of these earlier talks here. Then the statistics and statistical inference is this third kind of leg, because it's a matter of reasoning very much associated with classical probabilities. And the idea that reasoning and inference, according to the inductive accounts, are sound. And then the whole philosophy of statistical reasoning and the statistical method, meaning we don't say that statistics validates, predicts, or proves anything. We just say that the current theory we might have wasn't invalidated, mispredicted, or disproved. It's just bad reasoning to say that otherwise is statistics or probability theory. That's just that's bias confirmation. And not that there's anything necessarily wrong with that, because then that kind of reasoning can be closed and put aside. Instead of saying, well, we always have to be conscientious statisticians and probabilists and logicians and mathematicians and physicists, according to the theory of statistics and probability and the theory of physics. And then for reason is stuff that can be more Platonistic and ideal. So statistics has that as kind of like its gatekeeper and its door to being able to be said, okay, that's not untrue. Also, then gets into, as has been discussed here various times, there's approaches how to explain for these sample space and events and the ideas of random variables, how classical probabilities, and for the Bayesian, and then for continuous distributions and the non-classical or non-standard, yet meaning with real analytical character, real probabilistic and statistical character. These accounts for the laws of large numbers, then the limit theorems, besides the central limit theorem in convergence and emergence, that are to so hold and that do make for the numbers and the statistics after summary. That this sort of book called the Oxford Dictionary of Statistics helps introduce all these descriptive terms to help relate them to the formal accounts, so that then when the descriptive terms come into play, that they are as well associated with a very strict formal account. For this, such as Herbrand semantics, where we can say, hey, anything we can say in a formal language, an abstract symbolic language, we can also say unambiguously in natural language. So that's what this, I imagine, is about. An Art Deco table from about 120 years ago. Hotelling lolly trace. See multivariate analysis of variance. So ANOVA and ANOVAR are analysis of variance. And then multivariate is MANOVA and MANOVAR and MANCOVA. So there's a variance and covariance. So analysis of variance, analysis of covariance then gets into these different kinds of things with regards to the univariate, multivariate. It has individuals' brief biographies. Harold Hotelling, Hotelling, American statistician and economist. His first degree was a BA in journalism at Washington in 1919. It was interrupted by the First World War. Scheduled to fight in the trenches, his life was saved by a mule named Dynamite that broke his leg and caused him to be invalidated out of service. 21, he obtained an MA in mathematics at Washington and followed this with a PhD in topology at Princeton U. His first job was in the Food Research Institute at Stanford U, where he became interested in statistics. In 31, he was appointed professor of economics at Columbia. In 46, he was invited to found the Department of Statistics at UNC. He was president of the Econometric Society. He was president of IMS, and the REITs lecturer. And he was elected to the members of the NAS. So this just kind of gives his biography, but it doesn't really say what he did. But he apparently worked with Lolly and made the Hotelling Lolly trace. Hotelling T-squared. So students, Fisher's and T-tests are great little tests out of after the quadratic account that makes after the Poisson and the Gaussian distribution, all the bog standard stuff called statistics and college statistics for pretty much everybody. A statistic, and so the definition of a statistic itself is as regards to samples and statistics and a particular kind of statistic given particular kinds of distributions and their derivations. Having a multivariate distribution, which is an analog of the univariate star T distribution or T distribution. It's a multivariate distribution with an analog of the univariate T distribution. The statistic was introduced in 1931 by Hotelling. A sample of size n was drawn from a multivariate normal distribution with mean vector mu and variance-covariance matrix estimated as S. So the theory of probability today is all about those estimators and the maximum likelihood of the estimators. And then it's all great according to Bayes. But then as you get up after that into Jeffreys and Knight and the uncertainty of things, it flattens out and then gets different. If the column vector of sample means is denoted by x bar, the statistic t squared is given by t squared equals n times this quantity x bar minus mu, or usually the difference between the sample statistic and the mean of this, prime times s, that's the matrix -1 of x mu minus mu, x bar minus mu. For p cross 1 vectors, it's a linear algebra setup of this quantity n minus p times t squared over this quantity n minus 1 times p has an F distribution with p and n minus p degrees of freedom. See also Mahalonobis D. So there's Mahalonobis I heard a little bit more about, but this is just a great little thing. And here's the hypergeometric distribution. As is discussed here with regards to the hypergeometric in Gauss, is that Gauss, for example, came up with like means to describe the hypergeometric distribution. It's not unique. And so it's really kind of telling then that about the only thing that holds a hypergeometric distribution together is that its regular singular points are 0, 1, and infinity. But otherwise, let's see what's said about it. The distribution of the number of successes when sampling without replacement from a finite population, each of whose members is either a success or a failure. As an example, suppose that an urn contains n balls, of which W are white. Suppose n balls are taken from the urn at random without replacement, and let the random variable x be the number of white balls obtained. So it's sampling without replacement. Then x has a hypergeometric distribution given by p, that a probability that x equals r equals this quantity W choose r of this quantity n minus W choose n minus r, all that over n choose n, big N choose little n, with for r between 0 and W inclusive. The initial derivation of the distribution was published by de Moivre in 1711. The mean of the distribution is NW over N. The variance is NW N minus N, N minus W, and then over that over N squared times N minus 1. So counting arguments. Counting arguments are the greatest sort of thing for probability and statistics that are so. As after counting all the number of combinations and then counting which one of those match being according to the sample, and thus being able to define explicitly the distribution from which a closed and finite population arrives. For large values of n, the hypergeometric distribution may be approximated by the binomial distribution. See, that's kind of what you'd think of, I imagine, when it's like, well, there's only two possible values, on or off, or true or false, or yes or no, or black or white, or green or red from the possible samples, because then that gets into Ramsey numbers and coloring and arithmetic progression and Erdős's giant monster of independence, which means it's saying that there's different laws of large numbers which may apply. So as the book here notes, and it's appreciated, it's like there's an approximation to the binomial in the large, but it's not necessarily unique. There's always an error term associated with approximation. Since in this case, sampling without replacement is approximately equivalent to sampling with replacement. And that's whether it is or it isn't. Because you imagine when you pull out a ball and it's of a kind that whatever you sampled out of the vase deletes another one of the same kind from the vase or adds another one of the same kind from the vase. So sampling with or without replacement and sampling with or without regeneration or decimation or something like that. These could be different. These could be framed to make for different approaches. Hyperplane, an analytic formula for a plane. Independent events. Independent events do not influence each other. Fisher information. So Fisher, Bayes, Gauss, Poisson. These are huge names in statistics. The Indian Statistical Institute. The institute, which is located at Kolkata, was founded by Mahalonobis in 1931. It publishes the journal Sankhya. So Mahalonobis, let's take a look at him for a second. Daniel McFadden. Mauchly test. Markov process. Markov inequality. This is a great little book. Montel-Enzel test. Markov chain Monte Carlo. Andrei Markov. Marginal homogeneity. Simon-Whitney test, Mandelbrot, Benoit B, Maclaurin series, Maclaurin, Mahalonobis Prasanta Chandra, Calcutta. Indian statistician who is the founder of the renowned Statistical Institute. He studied physics. Mahalonobis was asked by a fellow student to express his opinion about an article in Biometrica. It was this encounter that stimulated subsequent research in statistics. Practical problems led to theoretical advances in many areas of statistics. It was an anthropometric problem that led to his distance statistic, d squared. So d squared then, briefly, very briefly here, the two-sample version of Hotelling's t squared. So as t squared we were just talking about was this estimate. And then the quantity d squared introduced by Mahalonobis is, it kind of from here, because I've been studying it briefly, the serial protocols on the usual bus today, and the differential pairs is the idea that, well, there's noise, and so we're going to emit two signals, and so this will help differentiate the one signal. It's like how that is like, are they different components? Is it the transform? Is it you've taken the transform and taken out the components? It's like, well, yes and no. It's just the signal and it's inverted signal. So the idea is that they go along together, and then if they're both adjusted by the same noise, you can just add and subtract the signals, and because they're symmetrical, it will delete out the noise. And so this is maybe kind of the same idea of this Mahalonobis d squared. It could be applied in a similar kind of setting. These kinds of things. With regards to distances and things like Hamming distance in words vis-a-vis the metric and norm, and here this distance in statistics, expectations, and the growing bounds of their error terms and their approximation. May be considered to be a measure of the distance between two groups of p-dimensional observations. Let x bar j be the p cross 1 vector of means for group j with s sub j, the corresponding variance-covariance matrix. So similarly as to the Hotelling, Euler, or whatever it was. D squared is given by d squared equals x bar 1 minus x bar 2 prime times the matrix inverse times x bar 1 minus x bar 2 without the prime, where s is given by s equals n s plus 1 plus n2 s2 over n1 plus s2, and n1 plus s2 are the sample sizes. So this reminds a lot about the linear fractional equation, which it is, and as is known here, the identity dimension is the envelope for both the linear fractional equation and Clairaut's equation and D'Alembert's equation in integral equations. That this here is then part of an account of working up an algebraic form then for arithmetic and computing these statistics. Colin Maclaurin is just fantastic, an analyst. Mallows, Lord Rayleigh, Rasch model, RASCH. A simple model that describes the probability that when a group of individuals ask a number of questions, individual J makes a mistake in answering question K. So this is a good model of uncertainty, because then you can add it up. You can use counting arguments, but you can kind of add up the opposite. So Rasch, it said, was a Danish statistician. He was the son of a math teacher. He gained his first taste for mathematics through reading his father's books. He joined Sir Ronald Fisher in London. He returned to Denmark. So Fisher is one of the great statisticians and probabilists. So let's see what they say about Fisher briefly. This is a great little book for somebody with some experience. Like, I have a college minor in statistics, and then I studied probability theory as part of a mathematics degree. And then I'm familiar with usual estimates to not lose and things like that. But then getting into it, there are many, many, many applied things because it's full of unknowns. The Holder inequality, that's been discussed here several times with regards to the triangle rule and Cauchy-Schwarz inequality and the Holder inequality. Hooke-Jeeves pattern search, Hopfield net. That would be familiar from the neural nets we've been discovering. Charles Hermite polynomials, the Hessian matrix. The Herfindahl index. Hidden Markov model, hierarchical Bayes. Sir Austin Tony Bradford. Heide, Christopher Charles. So Fisher here, according to the phone book algorithm. So Fisher exact test, Fisher index, Fisher information, Cremier Rao, Fisher Barons, Fisher distribution. Fisher information metric, Fisher lecture, Fisher linear discriminant function, Fisher's F distribution, Fisher's LSD, Fisher's Z transformation, Fisher, Sir Ronald Aylmer, arguably the most influential statistician of the 20th century. He virtually invented the subject of experimental design in ANOVA, which motivated his derivation of the F distribution. He's got some great writings on the science and philosophy of the thing. So statistics is another part of this, and it's largely underserved in programming because it's its own endeavor with regards to things like R, the programming language after S, for SPSS and SAS, the statistical frameworks and for statistical modeling, or for something like IDL, the programming language, not to confuse with IDL, the interface definition language. But those being one being about schema and the other being about dynamical modeling, that the science of statistics applies to every other science. So it applies to computer science as well. Facsimile imaging. So I think still today people would be familiar with the idea of the facsimile device because it enabled a copy of a paper, page by page, to be sent over telephone lines since a long time ago. And it was just the usual way to before there was email, there was fax, of course. And so, and with regards to stuff like couriers and the delivery of printed material, particularly in settings between parties at a long distance when it has to get there the next day or before. So fax is just something, I studied document imaging and fax, and so this gets into the CCITT, how they invented fax, how it works, how it goes over phone lines, how it makes compression, because there's much too much data to go over the phone line in any given number of just the plain bits. And so the compression was set up according to an entropy compression that they studied many pages of printed faxes because they were all alike and just as if typewritten pages. And so mostly blank white spaces, but just with all the letters and stuff in them, some diagrams. And then they have this geometric coding with regards to the G3 algorithm and the G4 algorithm, and with regards to G3 and G4 and one-dimensional and two-dimensional and run-length coding and the catch-up or the two-dimensional case to make it for so that then this is also used in all the document image scans. That's the same compression method that is used in almost all the document image scans that were made to scan all the world when all the documents in all the world were scanned over the past 30 or 40 years since high-speed scanners were invented. So then fax, besides then just like the fax and the preamble and the actual phone line noise that makes the facsimile document, all the things that go into the usual standard width of 1728 pels, picture elements. And then getting in the modern day with like, we'll just send it over the digital and these sorts of things about the International Telecommunications Union after the CCITT, the Community Consultative de Telephonique and Telegraphique, or as it may be. ITU Telecommunications Standardization Sector Study Groups. Network and Service Operation, Tariff and Accounting Principles, Telecommunications Management Network and Network Maintenance, Protection Against Electromagnetic Environment Effects, Outside Plant, Data Networks and Open System Communications, Characteristics of Telematic Systems, Television and Sound Transmission, Languages and General Software Aspects for Telecommunications Systems, Signaling Requirements and Protocols, End-to-End Transmission Performance of Networks and Terminals, General Network Aspects, Transport Networks, Systems and Equipment, Multimedia Services and Systems. So that's the standardization sector. Then the development sector has things like development strategies, development harmonization, management, and maintenance of telecommunication networks and services, including spectrum management. And then it gets into facsimile with regards to later and greater compression methods like JBIG and JBIG2, color facts, and with regards to at some point in time, facsimile, it was possible to fax color, and then today that's all just put into usual ubiquitous document formats and all such usual manners of printable renditions of things. And they're scanning. This is just a book called The Unix Network Programming, the Sockets Networking API. And so, because according to POSIX and sockets that and the internet protocols, that all the interneting is so similar. Then, with regards to stuff like the Internet of Things, as that may be, and its use of the much wider address range of Internet Protocol v6, like it's got 2 to the 32 times as many addresses, give or take a few orders of magnitude. Of the Internet Protocol v4, which had about 2 to the 32 possible addresses. Then, according to MAC and routing, media access control and routing and OSPF and BGP and all the different standards and all the different connections and the backbone that was built by the federal government to make it so that Ma Bell could run a phone company and these kinds of things. It's this Unix network programming today can just be abbreviated network programming pretty much. Then with regard to later and oncoming standards, like, well, sockets is sockets, but sometimes we'd have to do a handshake 3 times and we would just want to send packets and for our back end and our slice of the backbone, we just like to do this other way, like quick or after the other notions of using various approaches to setting up the handling and the routing and the transmissibility and then the retransmits. So for the kind of the guarantees of sockets and networking routing, that it's not going anywhere very fast at a blazingly fast rate in a huge volume everywhere at once. Is how it is. So that's kind of about the programming. That box of books was kind of consulted with regards to algorithms and data structures, networking and communications, types, and the great thing was types, statistics, and how it's always a science of statistics, including computer science. And then it can be to be so encoded, then gets into all the uncertainties and the unknowns and the scientific method, which is necessary to keep interpreting what may be an approximation that's usually not wrong with something that may have a formally large error term, say, or nominally infinite, or catastrophic, these kinds of things. That's just part of the idea then of software and the odds, say. So in the last few minutes of this episode of Logos 2000, as what I'll be planning to do is kind of figuring out a way to kind of finish Logos 2000 on a discourse, and I'll probably involve some reflection on the Christian tradition and the usual idea of that as a central figure of man with regards to mind, and then with regards to each other, the discussion of what logos is, because logos, the term, is kind of prehistorical, and then with regards to its relation to its most common dissemination has been in Western culture, then that's something to be accounted for a little bit and relayed. That is the central focus of that consideration. Here it's something just to be kind of be as a matter of reflection. So that's just kind of part of the outlook of this course, as it may be, about the study of these things. But then otherwise, after that, then what I kind of have an idea is to just start going through all these other books that I've collected, and this will be something more like book banter or something like that. I'm trying to figure out a better name than that, but it's not so bad. And the idea is that it will be just kind of unstructured and to reflect on the contents, while as well looking for these novel sorts of accounts. So is there any reason to listen to this or take this into account, these talks, these past few, say? It's like, well, there's the reroutine. You don't hear about that, or it's just a naive model of cooperative multi-threading that pretty obvious after you hear about it, but it's not necessarily something that is arrived at, and it's just not the usual way of things. Or then I've been looking at how to write an operating system, and so what that involves today is like kind of from the last discussion is like, well, what's the box? It's like, well, it's CPU and RAM and I/O. That's it, and then there's peripherals and stuff like that, or the surrounds. But then it's like today it's like, well, how's that going today? Isn't that more complicated? It's like, well, yes and no, and because it's kind of like it removed all the issues of trying to figure out how to do all the addressing and the interrupts and the memory I/O and the port I/O and this kind of stuff. It's not so much involved except to figure out like the North Bridge and South Bridge and the undocumented adapters and what to do with all these blobs and firmwares of the Wi-Fi and otherwise the apparatus or the networking stack bits or whatever that they're provided by the vendor, when really they as a matter of being scrutable, they'd be open source and these kinds of things. That actually today it's just like, well, you got to deal with the unified extended firmware interface, and if you actually want to get rid of that, you actually have to write to the timing of the DRAM. I mean, you got to keep the DRAM fresh and the memory, and then you have to write to the timing of the how one might say the PCIe bus, that the PCIe, their peripheral component interconnect, or the boards, expansion slot boards and all this, are bog standard, and in all the Intel and AMD and all the ARM personal computer offerings, and in the phones and in everything, that's ubiquity of economy and economy of ubiquity. That's just an idea about an operating system and how that could be. It's like, well, you can just start with universal extended firmware interface applications and then just kind of have that pick one or the other image for ARM or whatever architecture it might be. That then without further ado, it can kind of at least be something that just like, well, it's a headless runtime with a subset of POSIX, and it results you can run Java and other well-known enterprise runtimes on it because that's the only thing that ever runs on these nodes. So then it could just be the tiniest, fastest, newest operating system today. These kinds of things, Anyways, that's not new here. That's just the usual idea. I was like, well, yeah, that would be perfect. And then some of the other ideas, the 4 resources and the 4 facilities. That's like the database, the message queue, the web service, the file system. Anything you talk about as a resource must be one of those. That's not just a node or, the surrounds otherwise. So otherwise, yeah, hopefully this is just accurate. And then also open-minded, because there's stuff about it and stuff of these things. So let's take a sample from this next box of books and see what it might be. So grabbing at random the largest book. Oh, it's the New Complete Hoyle revised. But as a second sample, this box isn't all about card games. Oh, this is Hypnerotomarchia Polyphily, The Strife of Love in a Dream, by Francisco Colonna, translated by James Godwin. So this is literature. Okay, one more. Because these are mostly science books. Industrial calculating devices. So it's got a picture of an abacus and the slide rule and a kind of a meter stick thing on the front. By Wilcox and Butler. $25 it cost me. Out of Western Michigan University, Industrial Calculating Devices. Holt, Reinhardt, and Winston, 1962. The processing of information is as fundamental as life itself. It forms the basis of every rational decision, of every purposeful activity. It occurs to a greater or lesser degree in the brains of all living, rational creatures. The human mind is a complex and wonderful machine for storing and processing information, but in spite of its complexity, it has its limitations. To help overcome these limitations, man has always had to devise artificial aids to assist him in gathering, processing, summarizing, and interpreting information. In our fast-moving technical age, this need has become much more acute than it ever was before. So anyways, gentle readers, we shall also continue with this box next time. Logos 2000, 21st Century Foundations.